Hey, welcome back. This is Dr. Suchard, and in this presentation we're taking a look at some mixing incompatibilities of household chemicals. It's possible to mix some things together you find around the house, typically some cleaning products, because you figure if one cleaner is good, then more cleaning chemicals will be better, and you can inadvertently create a toxic chemical and hurt yourself. The objectives for this topic are that when you're finished with this video and studying any related course materials, you should be able to describe at least two combinations of common household chemicals that produce dangerous substances when mixed, to identify those chemicals created, and outline the signs and symptoms you'd expect from exposure to them. As already mentioned, the mixing incompatibilities we're going to discuss most often occur when different household cleaning chemicals are mixed. Bleach will be a common thread in this discussion. Bleach comes in various strengths, but typical household bleach is a dilute solution of sodium hypochlorite, NaOCl, at a concentration around 5%. Trace amounts of sodium hydroxide are added to adjust the pH to around 11. pH 11 is alkaline, but only mildly alkaline, so household bleach can be irritating to skin and mucous membranes, but it shouldn't cause caustic injury. That is, it shouldn't cause chemical burns. A small splash of bleach or accidental ingestion should only cause minor temporary irritation. Only with larger volume and or higher concentration exposures to bleach do we start to worry about corrosive injury. The reason for adjusting the pH to be mildly alkaline is to extend the shelf life, since hypochlorite will degrade if stored at lower pH levels. It's when the pH of bleach drops, as when it's mixed with acids, that we run into problems, since it will release chlorine gas. The sodium hypochlorite in bleach is in equilibrium with hypochlorous acid, HOCl, and sodium hydroxide. When you add acid to this, such as hydrochloric acid, or HCl shown here, it combines with the hypochlorous acid to produce water and yellow-green chlorine gas. Many toilet bowl cleaners and lime and rust removers that you can pick up at the grocery or hardware store contain acids. And you can easily imagine, for instance, someone trying to remove toilet bowl stains using bleach and then adding an acid, or the other way around. But any acid can do this, including vinegar, which is around 5% acetic acid and also used commonly for household cleaning tasks. Chlorine gas is a pulmonary and mucous membrane irritant. At lower concentrations, you'll get burning and irritation of the eyes, nose, mouth, and throat, and then you can begin to cough, wheeze, and have difficulty breathing, and if the exposure is high enough or long enough, you can develop pulmonary edema and die. The chlorine dissolves into the water on the mucous membranes and airway epithelium, where it undergoes the opposite reaction of what we just saw, producing hypochlorous and hydrochloric acid, which start to burn those surfaces, and inducing the production of superoxides and free radicals which extend the injury at a cellular level. Chlorine can be used as a chemical warfare agent because of these pulmonary irritant properties. Chlorine gas was first used for chemical warfare on the Western Front in 1915. It's just a matter of getting the dose high enough to incapacitate or kill someone. This could take many tons of chlorine being released in an outdoor trench warfare setting, but it would take much less, say, in a bathroom with a closed door or in a walk-in refrigerator, which are typical settings where mixing incompatibility poisonings occur. Here's a case example that occurred at a Buffalo Wild Wings in Burlington, Massachusetts in 2019. In the kitchen, someone had spilled Scale Clean on the floor. Scale Clean is a lime scale remover containing phosphoric and nitric acid. This was no big deal and the spill was cleaned up. Later on, per standard cleaning procedure, they used Super 8 to mop up the floors. The 8 in Super 8 represents that it contains at least 8% sodium hypochlorite, a little bit stronger than household bleach. Almost immediately, they noticed that the mopping solution turned green and started bubbling. Ryan Baldera, the general manager, attempted to clean up the area, but he was overcome by the chlorine gas, collapsed, and died. Here's a 1-minute video with some more details.
A mixture of cleaning products caused overwhelming toxic fumes that killed the manager of a Buffalo Wild Wings and sent 13 others to the hospital. According to a report from the Burlington Fire Department in Massachusetts, an employee poured the cleaner Super 8 on the kitchen floor of the town's Buffalo Wild Wings. However, an acid-based cleaning agent that had previously spilled in that area began reacting to the sodium hypochlorite in the other cleaner. Shortly after the employee started to scrub the floor, the chemical reaction occurred, sending him out of the kitchen with his eyes burning. The fire department reports that the manager stepped in and tried to squeegee away the cleaner. Overcome by fumes, the manager went outside, where he was later found by emergency crews who transported him to the hospital, but he later died. In a statement, Buffalo Wild Wings said it was, quote, shocked and saddened to learn of this tragic accident, and said it would be cooperating in the investigation. 13 others, including 2 customers, were also affected by the chemicals and were hospitalized, with at least 4 people kept overnight for observations. The Burlington Fire Department said a hazardous materials team later neutralized the area in the restaurant before turning it over to management, who will be in charge of any further cleanup.
So when bleach is mixed with acid, it produces chlorine gas. But when bleach is mixed with ammonia, as found in glass cleaners, it produces chloramine gas instead. Hypochlorite, OCl, plus ammonia, NH3, equals chloramine, NH2Cl. The same reaction that converts ammonia to chloramine can occur multiple times, next producing dichloramine and then trichloramine. The major product of mixing ammonia with bleach is chloramine, NH2Cl. The others are minor byproducts, so they don't play a significant role in mixing incompatibility poisonings. Chloramine, like chlorine, is also a pulmonary and mucosal irritant. However, it has better warning properties than chlorine, meaning that someone exposed to chloramine is likely to notice it earlier and/or at lower levels. If we compare the chemical structures, we see that chloramine is asymmetric and is a polar molecule, while chlorine is nonpolar. That makes chloramine more water-soluble, while chlorine is less water-soluble. Therefore, chloramine dissolves into the thin water-containing layer coating the mucous membranes and pulmonary epithelium faster than chlorine does, causing irritative symptoms earlier. Everything else being equal, someone exposed to chloramine is likely to leave the area sooner due to these symptoms. While someone exposed to chlorine won't notice it as quickly, they will breathe in and absorb more of the gas before they get uncomfortably symptomatic and are likely to have more severe effects. There's a lot of misinformation out there about what happens when you mix ammonia and bleach. The most common fallacy I've seen are reports that mixing bleach with ammonia produces chlorine gas. Yes, I know that chlorine and chloramine sound very similar, and that chlorine is the more familiar term to most people, but they're not the same thing. Some more chemically literate people say that mixing bleach with ammonia, in addition to producing chloramine, also produces hydrazine, N2H4, a rocket fuel, and nitrogen gas, and therefore mixing bleach and ammonia can cause an explosion in addition to the chemical risks. It is true that ammonia plus chloramine can produce hydrazine, and that chloramine plus hydrazine can produce ammonium chloride and nitrogen, but this only occurs at high temperatures and pressures achieved in the lab or in industrial settings. Just because a chemical reaction can occur does not mean that it does occur. And there are also many people claiming that mixing bleach with ammonia produces mustard gas, which is just crazy talk. This myth was popularized in an episode of King of the Hill from 2005, as we'll see here.
Well, the pressures of journalism can be very intense. Even I have felt it. But today, I really knocked one out of the park.
Good for you. What's the hint?
Okay, get this. I combined 2 common items in a powerful new way. I told my readers to harness the cleaning power of ammonia with the whitening power of bleach.
Ammonia and bleach? You told people to mix ammonia and bleach?
Only if they want bathroom fixtures that shine like the sun.
Peggy, that's the recipe for mustard gas. Arlen will be covered with a cloud of poison.
Ah!
This confusion probably stems from the fact that both chlorine and sulfur mustard, sometimes called mustard gas, were used as chemical weapons in World War I, and they somehow got conflated with one another. But they're actually quite different. Chlorine is indeed a gas, but it comes from mixing bleach with acids, not bleach plus ammonia. So that's error number 1. chloramine is not chlorine. And error number 2 is that chlorine isn't sulfur mustard either. Sulfur mustard is not a gas, it's a volatile liquid that can emit a poisonous vapor. Okay, the technical difference between a gas and a vapor is probably too subtle to get worked up about. But how is it that you're supposed to get mustard gas from bleach plus ammonia? Where would the sulfur atom come from? That's error number 3 in this myth. Next, to summarize what we've covered so far, we're going to watch some video clips of a YouTuber first mixing bleach with acid to produce chlorine, and then bleach with ammonia to make chloramine.
In this video, we're going to make chlorine gas, a useful oxidant. There are a few ways to make this. The simplest way is to simply mix chlorine bleach and hydrochloric acid. While this does work, it does not produce very much chlorine for the cost of reactants you'll be using. Also, the amount of chlorine produced is rather unreliable, as the bleach may be partially decomposed on the shelf before you use it. I need to cover a strange urban legend that too many idiots are falling for. A lot of people think mixing chlorine bleach and ammonia, or urine, will make chlorine. This is absolutely false. As you can see here, there is no yellow chlorine formation. But it is reacting though and producing many different products, so you still shouldn't mix ammonia and chlorine bleach, but understand that it's not making chlorine gas.
Warnings about the dangers of mixing incompatibilities often mention 2 further reactions with household chemicals. We've already covered the first 2 on this slide. In addition, multiple sources say that mixing bleach with rubbing alcohol creates chloroform, although we'll quickly see that this claim is not actually correct, and that mixing hydrogen peroxide with vinegar produces peroxyacetic acid. The graphic on the previous slide said that mixing bleach with rubbing alcohol produces chloroform, and that's not true. It's mixing bleach with acetone that makes chloroform, and it seems that some people are just confusing rubbing alcohol and acetone. Rubbing alcohol is typically a 70% or higher solution of isopropyl alcohol in water that's used as a topical antiseptic and can be found in many homes and clinical settings. Acetone is often used as an organic solvent and is most commonly found in the home in nail polish removers. It is possible to convert isopropanol into acetone by enzyme-mediated oxidation, and this happens in the body if you drank rubbing alcohol, but this conversion doesn't happen spontaneously. While there is a limitation on the shelf life of rubbing alcohol, that's only because the isopropanol can evaporate away, not because it turns into acetone. Some older rubbing alcohol solutions contain ethanol instead of isopropanol, and this seems to have been misinterpreted by some people who claim that mixing any alcohol with bleach produces chloroform. This is another situation like the mustard gas issue we discussed, where multiple errors were compounded onto an actual underlying truth. Mixing bleach with acetone makes chloroform, an organic solvent that used to be used as an anesthetic agent. Despite how it's depicted in popular media, chloroform does not rapidly knock people out. But it could cause CNS depression or other toxic effects if you were exposed to enough of it for a long enough time. And that's just highly unlikely to occur in an accidental mixing incompatibility setting. Mixing hypochlorite and acetone produces acetate, hydroxide, and chloroform. Now we're going to watch our final video clip demonstrating this reaction.
While we wait for the reaction mixture to cool and for the chloroform to settle out, let's look at how this reaction works. In this reaction, 1 mole of acetone reacts with 3 moles of hypochlorite ions from the bleach. This produces chloroform, acetate, and hydroxide. This reaction is known as the haloform reaction because it produces a haloform, which is basically a methane molecule where 3 of the hydrogens have been replaced by a halogen. As the reaction progresses, you can see the solution becoming white and cloudy due to chloroform in suspension. As a side note, this is a good demonstration to show why you should chill the bleach before adding the acetone. In this case, the mixture got hot enough to boil the chloroform produced. This would ultimately lead to a loss of yield and also a lab full of chloroform vapors. Another interesting observation in this reaction is that the yellow-colored hypochlorite ions convert to colorless chloride ions. Anyway, after a while, the chloroform settles out into a blob on the bottom of the beaker.
Mixing hydrogen peroxide with vinegar, a solution containing acetic acid, produces peroxyacetic acid. It is true that peroxyacetic acid, sometimes called peracetic acid, has irritant and potentially caustic properties. It's just that the same can be said about hydrogen peroxide and acetic acid too. Just because we are making a new compound doesn't mean that it is so much more dangerous than the reactants that we have to really worry about it. In fact, with regard to safety, peroxyacetic acid at appropriate concentrations is widely used in food and beverage processing to prevent microbial spoilage. And it's also used as a medical and industrial disinfectant. Part of its safety is that peroxyacetic acid spontaneously breaks down in water back into hydrogen peroxide and acetic acid, neither of which are particularly toxic, and they're not environmentally persistent. While accidental chloroform or peroxyacetic acid creation may well occur from mixing household chemicals, reports of injury or death are so rare that I was not able to find any when preparing this presentation. These are interesting theoretical risks of no apparent consequence. This is in contrast to the significant risk from mixing bleach with acids or ammonia, which routinely cause minor inhalational injuries and occasional deaths. I've seen several people in the emergency department due to these mixing incompatibilities. And that's it for mixing incompatibilities of household chemicals. I'll be seeing you around.